So now we have to cover all the rest of the material in one lecture. So we still haven't gotten to the point that we have maybe I'll take a direct sum of the rank homology. The graph, so K goes from 0 to n. Rank homology of T star Grassmannian k-dimensional plane from here. And there should be some relation between this module where T, so T is has this C star, these scales to tangent directions, and then contains matrices n. So this is maximal torus in GLN. Maybe I'll write just A. So this is in GLN maximal torus. So there should be some relation between this and tensor product of evaluation representations. Where for this Yangian of GL2, where so this is defined using this R matrix, which is 1 minus H bar over U, permutation of the factors. Because this defines, in this space, defines an action of the Yangian. And so this is where we discussed, this is where this quantum spin chain lives. And there should be some relation between this and that. In particular, such that the quantum cohomology here has something to do with the spin chain. So we haven't gotten to this point yet. And so now, in doing so, in fact, it will be instrumental to think about first. So here we look at here we have these operators. Here we have these transfer matrices. And what are these transfer matrices are? Well, you take the trace, so there's some transfer matrices, and we took the auxiliary space to be also C2. And so what this thing is maybe we give it a parameter U if you want. So then this is so this is the trace over this auxiliary space of we act in the auxiliary space by the matrix 1z, and then so tensor 1 times the R matrix of this C2U. And here we take the product of C2AI. So what this R matrix really is the product of R, as we discussed, R01, R02, so let's take R. So these operators here commute, and they will have something to do with the quantum multiplication on this side. And so to help us with the identification, it's useful to think about first the case of here classical multiplication, so classical cup product. This is the case when z equals 0. And so, which is not normally the case considered here, but there is nothing in this formulation. There is nothing that prevents it. We can certainly can can't take z equals 0. There's no problem. So when you impose boundary, when you think of some boundary condition and the like, this is a bad idea to identify things using this identification. But if you think of these operators, you certainly can plug in. You can certainly plug in z equals 0. And so we would like, if there is a match, we would maybe start by matching so this will be a family of commuting operators here. And we would like to think, well, where would the eigenvectors of these operators go? And so here, if we look at this side, you see that the operators at z equals 0, it's an elementary exercise. So I should have added to the list of problems, but you maybe have enough problems. Something you should just convince yourself: the transfer matrices become triangular with respect to lexicographic order. The standard basis. So the standard basis on tensor product is like, some sequence. E1 tensor, E2 tensor, E2 tensor, E1. Something like that. So you just, in a tensor product, you have if you pick a basis, if you take a standard basis, the basis in which this, maybe take some standard basis, and the basis in which this operator. So this operator is written in some basis, you pick that basis, and you take the tensor product, and so then these operators are triangular. And triangular with respect to lexicographic order, when you think about lexicographic order, that corresponds to a certain ordering of coordinates. Right? You have to, here, in this expression here, you see there's an ordering. In the original physical formulation, the spins interact with neighbors, so there's some ordering. And this ordering is even more important once you take the z equals 0, then there's no cyclic invariance anymore. You really order. And so then this is some order thing, and that with respect to some ordering, if you read it from here to there, then this is operator triangular. Now, on the other hand, if this were to go here, then we certainly know what are the eigenvectors of cup product. So if I take a covariant, if you take a covariant cohomology of any variety, then the operators of cup product by the classes in covariant cohomology, they have in general Jordan blocks corresponding to the cohomology of the fixed components. But in this case, the fixed components are just points. So remember the spectrum. We had this picture, the spectrum of covariant cohomology. So this is a bunch of linear subspaces. In some fashion, and the functions are just functions. You just multiply by functions, okay? And so then the delta functions on the components. These are the eigenfunctions, functions of the operators of cup product. So the eigenfunctions of multiplication of product are equal to just classes. I mean, this is really over a ring, so you can take the equivalent homology of the point times the class of the fixed point. So if I multiply fixed point by any class, I just get the restriction of that class to the fixed point, which is in here. And so in the current K-theory, if I have a fixed point, then if I tensor multiply by any bundle whatsoever, I just get the restriction of the bundle to that point, which is an element in my ground ring. So this says that the eigenfunctions, and this is irrespective of any ordering. This is somehow there's no ordering involved in this. This is just Grassmannian. We didn't have to pick any choices. Canonical of these guys should be, so this should correspond up to some multiples. This should correspond. So the fixed points correspond to eigen vectors of transfer matrices of T z equals 0. But it's a more interesting question then becomes, and that's see how then more interesting question is that if I take this standard basis here, what will it correspond on this side? So, in other words, the map, in other words, the identification, we almost, up to some multiples, we almost know what the identification should be. We just have to make fixed point to sum up to some multiple to the eigenvectors here. But it's easier to discuss the kind of sillier problem, maybe, is to take a coordinate basis, which is, well, you don't think much about the coordinate basis on this side. But to tell where that guy goes, it's kind of a more interesting question. Well, and the reason that question is important is because on this side, so this is a basis which is evidently, but just by its very construction, is compatible with the tensor product. And the tensor product is precisely the structure we would like to find on this side. So maybe to reiterate, so just we'd like to match two sides of the story. On one side, it's the standard basis is given, and the eigenbasis, well, in general, for general z, it's something complicated, but for z equals 0 is something which can be defined over our ground ring, and this is really triangular with respect to this guy. And on the other side of the story, we very clearly see the eigenbasis, and we don't see so clearly yet the standard basis. And the standard basis we'd like to see. And then there's something I already said, but maybe it's worth repeating, is that here on this side we don't see any ordering yet. right? We just have Grassmannian, and there's everything is completely, instead of, we could have just as well worked in G-query cohomology. Somehow we didn't know the ordering yet. And these fixed points are defined. Okay, sorry. Of course, you have to pick the set nonsense. You have to have fixed points. You need to pick the torus. So you have to pick the torus, but there's no ordering of the tensor factors yet. But on this side, the ordering starts from the very beginning. So we somehow have to see the ordering there too. And the answer is already already in the work of Nakajima. So this is the way you think about this tensor product is not, you don't really match the tensor product to the whole cohomology. You match the tensor product to the cohomology. So the way you see the order is you pick a general one-parameter subgroup in this A, or you can say that this is, you pick a choice of attracting or repelling interaction, and you match the tensor product with the cohomology of the attracting manifold of this fixed point. And so this is how the ordering is going to come in. And so then so maybe at this point, I've given enough motivation. Maybe you can say, you can just take at this point, maybe it's enough to take a guess. The standard basis. So maybe before, so I'll take. So if we choose ordering of coordinates. So maybe I'll write it like this first. Still on this board. Here we have here and here and here. It's important to have this ordering of coordinates. Tensor factors. It's something which enters this notion of lexicographic order and enters here. And the corresponding notion on this side would be, so the notion that corresponds to this is a choice of attracting / repelling directions. For this torus, it's the torus that acts preserving the symplectic form. And i.e., in other words, i.e. a choice. Choice of a general one-parameter subgroup. So what does this choice look like? So here is my here's my x, and I have some fixed point. Now at the fixed point, my torus, since it preserves the symplectic form, it will have some attracting, some repelling directions. It's a general theory is going to look like this. So once I've picked a one-parameter subgroup, there'll be some directions that attracted, there'll be some repelled. And so in particular, there'll be this attracting manifold. So if I have a point, fixed point P, there'll be the attracting manifold of P. Which is a Lagrangian submanifold in X, because it's just some Lagrangian, it's holomorphic Lagrangian in X. And what it is concretely, so you did, I hope so, you did the exercise about Grassmannian itself. Grassmannian itself, you apply this idea to Grassmannian itself, you get this, the Schubert cells are the attracting manifolds or fixed points. And so this guy concretely is a conormal bundle to the Schubert cell. It is isomorphic to linear space, but that linear space is really conormal T perp to Schubert cell. And then if I take its closure, in its closure there will be some other fixed points. It could be some other fixed point, P prime, that belongs to the closure of the attracting manifold. And then this will have its own attracting manifold and so forth. You have this kind of specific, so this, if you take the, in other words, if you take the, you can define something like the full attracting set, like full attracting set of P. It's the transitive closure of the relation being contracted. So it's a union over all P prime less than P in the partial order. So attracting defines a partial order. You take all the littlest one, you take this. Attracting P prime. So this is a closed. Closed, singular, Lagrangian submanifold. And so then a guess would be, so maybe an educated guess, is that the standard basis corresponds to some actual Lagrangian, some element goes to some actual element. Some element in some Lagrangian in here, so in H of this full attracting set. So standard basis, this corresponds basis element corresponding to this point P. These basis vectors are in bijection with 6 points. Because and so this corresponds to some element in the full attracting set. So in fact, some represents a Z-linear combination of Lagrangian submanifolds of Lagrangian, so Z-linear combination of components. And then, so if this is a guess, then we can verify it immediately. So, so how are we going to verify it? So this is some linear. This is the direct sum of Z times component. Class component. So in other words, this is something with Z coefficients, which is very constrained. And how we can characterize this guy? So my point is that this is enough to characterize. This has unique characterizations. It can be uniquely characterized. Characterized that it's so whatever this whole story, it becomes trivial if H bar is 0. If H bar, so if you have if you take so the this so if you have a quantum group, well, the Yangian in this case, then so you define this box or subalgebra corresponding to some element in the Cartan. If that Cartan element degenerates, what you get is like the Yangian for the Cartan subalgebra. And if in addition you turn off H, this becomes really diagonal. Then this goes to a loop algebra, and this goes to a Cartan in the loop algebra. In other words, if you take, so this element is the non-trivial matrix element divisible by H bar. So if you take out H bar, but then work module H bar square, then this operator becomes not only triangle, but in fact diagonal under B. So if you kill H bar, you already, so we divide out by H bar to get somewhere. Everything, all non-trivial elements divisible, all the non-trivial matrix elements divisible by H bar. But then if you then work kill H, if you then set H bar to 0, then you get diagonal. So this means it's uniquely characterized that by the fact that mod H bar equals proportional to fixed point. Fixed locus. Fixed to proportional to just P itself, to the class of P itself. And why is it uniquely characterized? So there's in fact a better. So instead of thinking of this, there's a better way of thinking. So if I take, so maybe we'll take it. Maybe we denote it since it's called the stable envelope. Let's just call it step P element in here. So take step P. So step P. If you take step P and restrict it to any. So maybe some step. P restricted to any prime, then maybe I'll fix how about I fix I fix normalization to begin with. So let's say it has to, well, no, maybe we'll get this one. So step P restricted to prime. Then this is an element where this is Lagrangian class, so it's an element in 1/2 dimension x. Sorry, dimension x. I forgot they multiply by 2. Dimension x equivariant of a point. Okay, so concretely, it's a polynomial of H bar A1 through AN of degree equal 1/2 dimension x. If it vanishes mod H bar for P not equal, so this says that this polynomial will have to be divisible by H bar for P not equal to P prime not equal to P. But this means if it's divisible by H bar, then the conclusion is that the degree, so the conclusion is that the degree of this polynomial in the variable A is less than what it could have been. So it's less than the correct bound is 1/2 the codimension of fixed locus. So if I have some Lagrangian subvariety, in general doesn't have to be fixed locus, doesn't have to be a point. So then the degree in A can be at most this, but in fact if it's less, then it's this important condition. And so now if I start, so this the basis is normalized so that it starts with plus minus 1, the actual class of attracting manifold plus correction, and then plus minus 1. So in this lecture, consistently I've been glossing over signs, and since there's plenty of signs, and getting them right is important. There's some yoga how to do this, but we'll just skip that. So now I'll claim that there's a unique such class. I mean, here you can put an integer, doesn't matter which one, but the right normalization is to put plus minus 1. And then there's unique such class that satisfies this bounds. Well, because you see, if I have any class supported, so if I have, suppose I have class, let's start with the, let's imagine I have 2 such. And then if I take their difference, I'm going to get a class which is supported, which is now supported. They start the same way, but now let's say it's supported here. What does it mean supported here? It means it factors through the inclusion of this fixed locus here. The inclusion of this fixed locus already contains multiplication by all normal weights. And this is a polynomial. Multiplication by all normal weights is a polynomial of this degree, of this degree. Okay. So no class restriction of which has less than this degree can be supported on this. Is that clear? So maybe one more time. Suppose I have 2 different stable envelopes, and then I take their difference. This is some class which will now be supported on the full attracting set of some smaller fixed points. And so then okay, what does it mean? That means if a restriction to this point factors through the inclusion of this fixed locus. And that means it's divisible. It's divisible by a polynomial of degree exactly half of the codimension. So, it's a polynomial of degree 3 cannot be divisible by a polynomial of degree 5 because there's non-zero divisors here. So it's a unique such class. And it's conversely, it's not that difficult. In cohomology, it's not that difficult to prove that such class exists, especially here. For Grassmannians and similar, in fact, all Nakajima varieties, what you can prove is you can do this. You can take a generic affine deformation. If you take generic affine deformation, then what will happen? A generic affine deformation. This will be the generic affine deformation can be taken A invariant, A equivariant. There are no curves in the generic affine deformation. So generic affine deformation, the attracting manifold is already closed because it has no room to break. There's no complete curves in the affine manifold. So you have a cycle, attracting cycle. You can just close the cycle and take I have a cycle in the generic fiber of the family. You close it and you get a cycle in the middle. And that cycle, you can check that it's a Lagrangian cycle supported here, and that cycle will be divisible by h bar because, its restriction to any point other than p will be divisible by h bar because if you kill h bar, so it means you can work. If you kill h bar, you forget about h bar equivariance. If you forget about h bar equivariance, you can. Just A equivalently, you can deform. If you can deform a cycle of a point, its restriction is 0. So that's but there's a better, somehow the better proof. There are proofs for you can, in fact, have proofs for category of coherent in dB Koch, where you can just really construct this thing inductively. You start by some kind of Euclidean algorithm. You can really construct this thing. and also this. I mean, anyway, there's some notion of how you can detect the cycles. But now, and so what is this thing is? So now maybe we'll do first an observation and do example, and so the an observation is that this guy. So what is the R matrix? The R matrix is the intertwiner between the tensor product and the opposite tensor product. And this is divided. You have two notions of the tensor product and the opposite. Now the tensor, what does it mean here? Here you take one choice of attracting directions. And here you take the opposite. And so then you get an intertwiner, and that intertwiner is the R matrix. So what is constructed? So you have maybe let's do let M1 be the current cohomology, so this is current cohomology of the union of Grassmannians from to N1 Grassmannians K1 K N1, and then M2 is similarly same notion. Then if I take M1, M2, then the first by Kunin, this is the cohomology of a fixed locus inside so maybe sorry, forgetting T star. Maybe how about I have an abbreviation TG, and this is the union of T star. Otherwise, we'll just be writing this to the end of the lecture. Kn. So I take here is TGN 1. TG N1. And then TG N1 plus N2. Fixed locus to A, where A in this case is just a one parameter subgroup which acts by 1, 1, 1, A. And 1 of this, and 2 of this. And then this is a fixed locus, and by a similar construction, this works if the fixed locus, if this bound makes sense with the fixed locus of point or not point. So this would be by this stable envelope. This will go to the cohomology of this whole thing. First attracting locus, this is an isomorphism. So this is an isomorphism to the attracting locus. and then this push forward is an isomorphism of the localization. As I said, this notion that the tensor product is cohomology of attracting locus, this is already played a very important role in Nakajima's work. And so now what does it mean to take the opposite coproduct? In the opposite coproduct, you change, what does it mean? The change of the ordering corresponds to the change what I consider to be attracting or repelling. So then I take, so this means if I make the opposite change, I take like unstable envelope. Then this goes to the cohomology of the repelling locus. And this is also isomorphism after localization. And so then if I follow this loop then, this would be saying, how do I put the two factors in the opposite order? So this is a rational. This is this loop, which is the R matrix. So the R matrix is unstop inverse composite stop. And so this is an element. This is endomorphisms. This sits in endomorphism of my fixed locus. But there's localization here, so I tensor the rational function. Which is what we wanted, right? We wanted to have this. We wanted to have a braiding. Here's the braiding. The braiding is rational. Is it supposed to be? And the fact that it satisfies Young-Boxer, this is a consequence. So Young-Boxer and everything is a consequence of something called people call it triangle lemma. Means suppose I have a torus acting on X, and I have so I have a torus and I have a subtorus. Then correspondingly, I have inclusion of fixed loci. So I have the fixed locus for the largest torus sits inside the fixed locus for some smaller torus, and this sits inside X, which is the fixed locus for the trivial group. And so then you can ask for this kind of stable, so between the cohomology. Well, I'm not going to write the cohomology. I'll just write it itself. And so then there's a stable envelope for the big store. There's a stable envelope for A. There's a stable envelope for A prime. And then here, there's a stable envelope for the quotient. And the triangle lemma says that this triangle commutes. And how is it proved? Is because, well, in my definition, it's something like this. Sorry, I forgot the definition. So I erased the definition. Oh, no, here. And it says that if I multiply two matrices satisfy this condition, then the product also satisfies this condition. And therefore, we have multiplied two matrices of diagonal elements of which satisfy some degree bound, then of course you have the same bound for the product. And this implies Young-Boxer and other things. So let's now do an example. So what is it for? So in particular, this triangle lemma really implies the kind of thing that if I want the R matrix with take a space and a product, then this is the product, the ordered product of R matrices of individual guys. It's this sort of thing. This is a consequence of this. And so if you want to braid a representation with a product, it's enough to braid it one at a time. And this is a function for this triangle lemma. So let's now do an example. This is getting really warm, so maybe I'll. So what is if I T star P1? And what does this look like? So this looks like my picture of T star P1, and there's a P1 itself. Maybe this point is 0, this point is infinity, and then there are the cotangent fibers. So this is like this really is a toric picture of T star P1. So this is P1 itself. This is the cotangent fiber at 0. And this is the cotangent fiber at infinity. And now, let's suppose the attracting weight here is such that P1 is attracted to 0. And since it's preserved, the symplectic form is preserved, that means attracting here means repelling here, and so attracting there. So, therefore, the stable envelope of infinity, well, it's not so many choices. It has to be plus minus. So the only thing that attracted to infinity is the fiber at infinity, so it has to be plus minus the fiber at infinity. And the let me not explain how you choose the sign. And it's easy, but it's just some extra piece of information. So, and then, more interestingly, what should be the stable envelope of 0? So the stable envelope of 0, well, this has to start with let's say, it starts with P1 itself, plus with some multiple the cotangent fiber at infinity, where m is an integer. And so what's the condition? So if we restrict it to the infinity, we should get something. We should get a polynomial. So if this is let's say the tangent weight here is a, and therefore here is minus a. And if it's 0, if it's a at 0, then it's minus a at infinity, and a is there. So then we get restricted to infinity, we should get the polynomial in a of degree less than what? Half of codimension is 1, so it has to be of degree 0. The bound is half of the codimension. Half of codimension is 2, half of 2 is 1, and so less than 1 means 0. And so, okay, so what is it going to be? If we restrict the restriction of a manifold of a smooth manifold to a point in a credit homology is a product of normal weights. And so this is the first guy is going to give us. So if restricted to, first guy is going to give us a, and the other guy is going to give us minus a. So m times minus a. And so from this, the conclusion is m equal to 1. And the reason m has to be equal to 1, well, you can see. Well, what's a nearby, what's a trajectory that goes near this attracting trajectory? Well, it's going to go like a hyperbola, right? So if in other words, there is a deformation of T star P1 in which the attracting manifold of 0 is going to look like attracting manifold of some nearby point. Attracting like the orbit of some nearby point, this looks like a hyperbola around infinity. And so if I degenerate, the hyperbola goes to the union of two axes. And so this means both is coefficient 1. All right, and then if I change the attracting direction, you get the opposite picture. And so what is then this stop? What is then stop? Maybe I'll continue here. So if you want to compute unstop inverse composed with stop, it's easiest to compute. So first you compute the restriction to fixed points, stop composed with restriction to fixed points, and then you compute the unstop, the composition restriction, unstop fixed point. Yeah, everybody agrees? So this is the restriction back to fixed points. So what is this matrix? So this matrix is, so now we're doing in full equivalent homology. In full equivalent homology, all fibers, all cotangent fibers now going to pick up an extra weight, which is minus h bar by convention. So here's minus h bar, and here's minus h bar. So restriction of 0 to 0 it's a normal weight, so it's minus a minus h bar. And then restriction of this guy, restriction of this guy to infinity now going to pick up an extra minus h bar, right? Because you have to, instead of summing minus a and a, you sum minus a and a minus h bar. So minus h bar here. And then the other guy, well, I didn't tell you what the sign is. Maybe the sign is minus. Maybe I'll consult my notes on this. Yeah, I think it's minus. And so then you get minus minus a, and so you get a. You get 0. And so the two matrices you need to multiply, therefore, are minus a minus h bar. The other one is just you turn everything around, so then it becomes a minus h bar, so the inverse of that times this guy. I'm just copying it from here. And you know, I don't know how to multiply these matrices other than just do it. Yeah, there must be some clever way to do it. Just I don't know what it is. So this is going to be a over a minus h bar minus h bar or a minus h bar. Well, I guess you can, I don't know. Easier to multiply. And so what this thing is the middle block. So if I take 1 minus h bar over u times the permutation, now I'm free to multiply the R matrix. If you take an R matrix and multiply by any function of u, you still get an R matrix. So I'll further multiply it by this, so that the purpose of this normalizing the R matrix like this is to have it 1 on the invariance. If this permutation has 2 eigenvectors, eigenvalues +1 and -1, you can make the R matrix to be 1 at the invariance. And so this is acting. So this guy acting on C2 cross C2. So this C2 cross C2 has 4 eigenvectors. So there is, like E1 cross E1. This is an invariant, so on this will be 1. Then will be E1, E2, E2, E1, and then E2, E2. E2 is also invariant, so this is 1. And on the middle thing, the 2x2 block is this block, right? With the identification where U is A. And this is, that clear? And so this proves that so what is C2 cross C2 for us? C2 has to do with C2 has to do with TG2, the union of Grassmannians. So this is a point union T star Grassmannian of one-dimensional subspace and two-dimensional space. It's what we just analyzed at P1, and then union another point. So this in this TG, the two extreme values of K are trivial. They're always points, and so there's a point and point here, and non-interesting guy here. And of course, you're not going to get anything but 1 for the point, which we got, and this is interesting for T star P1. Okay? And by this formula here, we're done, because all our matrices are just expressible in terms of this. If you know how to braid 2 factors, you know how to braid any number of them. And so this finishes the identification of whatever you get somehow. The geometrically constructed R matrix is the R matrix for the Yangian of GL2. Okay? So in general, so this T star Grassmannian is an example of a Nakajima variety, and Nakajima variety corresponds to quivers, and quivers come. There's 3 kinds of quivers. It's like this classification of, you can classify anything you want like this. So if you take 2 cases you know best, and then none of the above. and so the classification of quivers are the quivers of finite type, of a fine type, and none of the above. And for any quiver of finite type, you're going to find you will find the R matrix for the. If you do this, you'll find the R matrix for the corresponding Yangian of a fine-dimensional ADE Lie algebra. And for the affine type, it gets slightly more interesting. And for the wild type, it gets really, really more interesting. So interesting that we don't understand anything about it. So, at least I don't. So it's some really, I don't know. I'd like to say some really new solution of Eilenberg's ring. But they act in spaces which, here it's nice that we have some a priori picture of the space in which this is supposed to act. And there, the space is, yeah, I don't know. It's not so clear what a priori picture of that space is. Right. And so then very generally it can be shown that in all of these cases, even when we don't understand we don't really understand what the Yangian, or what is even the Lie algebra is. So the construction, how you forgot to say yesterday, is that if I have an R matrix, how do I at least know what the Lie algebra? And the Lie algebra comes with an R matrix, which is what we decided. So R at U is is 1 at the infinity, so it starts with 1. And all non-trivial elements of that are divisible by h bar. So the next term will be h bar over u times something, which is in general denoted some linear part. And then plus h bar times something called capital of 1 over u square. So here, the reason that we got in this R matrix here has only linear term with 1 over u, just because representation is so simple. If you start multiplying, if you have matrices that only have linear terms over u, if you start multiplying them, of course you're going to get more terms. It's in general, for general braiding, this particular role is played by 1 over u term, and the coefficient of this, you can show from Yang-Baxter equation that the coefficient of this guy, the same way you define the Yangian to be span of the coefficients, but the coefficient of this part is a formal Lie algebra. So it's a consequence of Yang-Baxter equation. So it's a Lie algebra. So in general, what even for a wild quiver, there's also only partial understanding of what that Lie algebra is. This is a very interesting Lie algebra, but it's far from obvious. But whatever that Lie algebra is, you can prove abstractly a similar relation between. So we've got the formula. What do we have? The formula. We had a formula for we have a quantum product. So the quantum product. All right. So when x was T star Grassmannian, and lambda was in h upper Q of x, and let me denote we had to denote something the class of the line. Let me now call it alpha. So alpha will be the class of the line. So this is a generator in h lower 2x z, class of Fluker line. And the formula for the quantum product by lambda, formula we had, it has to do with the cup product, minus h bar. Here comes, you pair alpha, and it has to be linear in L, so this is the natural pairing of these two spaces. Then there's z alpha 1 minus z alpha, and then comes f. So for general Nicodemus variety, what you get is this guy. This was z, and this is what it is. It's the root lattice of certain Lie algebra G, you can start from there. So which is consistent for T star Grassmannian, the Lie algebra is GL2. And its roots are really, it really is that. And then this Lie algebra G has a decomposition where we have the Cartan subalgebra. The Cartan subalgebra, incidentally, has something to do with h upper. This is an element. This is the Cartan subalgebra. Well, assuming the well, anyway, doesn't matter. And then this has Cartan decomposition. So the sum over alpha, G alpha. So this is like H over 2 of x. And so there's a natural pairing between the root should be a linear function on the Cartan subalgebra. So this is what it is. And so then, so in general, what this thing gets promoted, this thing becomes sum over positive roots. So positive in the sense of effective curve classes. So if you think of this, here's a cone of effective curve classes. And then you take same expression. This again makes sense. This is what the in the coefficients of the quantum multiplication. We really take like z to a root curve class, and then this you replace by the by the canonical tensor. And G alpha. So these are dual. So this guy with respect to the pairing is dual. So then you have this. You see, if you have something, if you write something as matrix elements of a matrix, then you have a pairing between. So if you have a matrix and tensor product, you can take its span of in one tensor product and span in the other tensor product. And then these two spaces will be canonically dual, because you canonically given an element in the canonically pair by the element given. And so this is the pairing that this gives you here. And so right, this like takes a takes a while to prove this. It's not this proven for Grassmannian by inspection. It's proven through some kind of song and dance, and then you can prove that this really is. So this is the 1 over u square coefficient of transfer matrix up to a constant. One over u coefficient of a transfer matrix is not so not such an interesting thing. It's because and right in general this way is interpreted inside the Yangian. I forgot to say this is something very so another interpretation is that it's not another interpretation. It's just something I said, but maybe I didn't stress so. So remember at the very beginning of this lecture, we had a discussion of how transfer matrices turn into the operator of multiplication in cohomology. So what was there? We took some matrix, some general element in the Cartan. So we took like a trace of 1, z, r, this sort of thing. And we then set z equals to 0. So it means you act by some element of the Cartan, so this is tensor 1. And then you take that element to 0. It means this is a projector. So if you if I act by Cartan, and then you take that to 0, you're going to get a projector to the lowest or highest, depends how you order, to either the lowest or the highest weight vector. Right? The eigenvectors, Cartan is going to be diagonal in weight vectors, and if you send the element to infinity or to 0, this means you go to some extremal weight, highest or lowest. Okay? So that says, so this means that in general the vacuum, maybe call it vacuum, like a vacuum vector. So this says that the vacuum matrix elements of the R matrix are operators of cup product. So this is z equals 0, this becomes like R vacuum something, vacuum something. And so these operators are operators of coproduct. That makes sense? And so in particular, this guy sits there as some 1 over u square coefficient. So this whole thing is it comes from some 1 over u square coefficient. From 1 over u, you get something, just Cartan itself. And from 1 over u square, you get the coproduct with non-trivial divisor. Because the whole thing is graded. So the R matrix has homological degree 0. So if you extract the coefficient of 1 over u, you're going to get something which has homological degree 1. But it has to be divisible by h bar. And so it can only be homological degree 0. And so then you get, means something, some constant connected components. This is how Cartan elements here. These Cartan elements, they act by, so these guys act by linear functions. Act by linear functions of the dimension vector. So the linear functions of W, this is center, and this is an interesting part of the Cartan. This is with that. And but with 1 over u square coefficient, you still be divisible by h bar. So you'll be left with operator of cohomological dimension 2. And that 2 has to be, if it's in a classical multiplication, well, it has to be multiplication by divisor. This is what it means to be in cohomological degree 2. And here, if it's in this part, for non-vacuum matrix element, it will have to do with the quantum correction. Okay? Right, so there's this, right. And I should say that connections in general, this sort of thing, if I write a connection like this is called a Casimir connection. And this is, you can find discussion for fine dimensional Lie algebras. You can find discussion of these connections in the work of Toledano Loredo, for example. Toledano Loredo with different co-authors. Also Varchenko with different co-authors discuss things like this for Java. So this sort of sorry, I said connection, but I mean quantum differential equation will be the Casimir connection. I'm not going to talk. In fact, I will talk about the quantum differential equation now. Because, so what's the contribution of geometry to the study of this? I mean, there's several contributions, but one clear contribution is that geometrically it's very easy to tell what are the eigenvalues of this operator. Eigenvectors, this is harder. So, but about eigenvectors, in fact, I'm going to give a talk Friday, December 1 in the representation theory seminar. But for eigenvalues, we will have that. Now to connect this, somehow to bring it back to the problems of bit ansatz, I will now explain how one computes the spectrum of these operators. So. Maybe I'll take a drink of water. So we're going to something called quantum differential equation. What is this thing is a flat connection on H2x. People call it small. No, this is big enough. This is this is interesting enough. So on H2, it doesn't matter. Maybe C coefficient doesn't matter with fiber. On a trivial bundle with this base with fiber, big rank homology. X. Let's also take it C. And its flat section look like this. So if I take, so I have one element over here, and d by d lambda of some unknown function psi of z, this is the quantum product. Where d by d lambda of z to the d, this is you pair lambda with d, take z to the d. In fact, if you count cohomological dimensions, this is not so good because this is here you have something of dimension 2. I mean this whatever dimension of that this goes up by 2, so it's good to add a variable here, which you think of having degree 2. And for any such, so this is the basic result of the Brovin, I think. So this is flat for any epsilon. And so now if we have a differential equation of the form, so let's say I'm in one, like for Grassmannian, let's say it doesn't matter, I can take do the equation in one variable, and this d by d lambda is z d by dz, so I get z d by dz of some function psi z equals some matrix. What do we call this matrix? M of z c of z. This is like the most basic object. It's a linear differential equation. In fact, it's not important. It's not important for what I'm going to say now, but it's interesting to know that this equation here has regular singularities. Because if you look at here, you see it's first order poles in variable z. And also from z d by dz, you get singularities at infinity and 0 to infinity, so that has regular singularities. It's nicer to have equations with regular singularities. I think it's nicer to have equations with regular. People who like Stokes data, they think otherwise. But I think it's nicer to have equations with regular singularities. But it's not important for what I'm going to say. So if I have an equation like this, and I send epsilon to 0, this is like the it's like a basic asymptotic problem in all of analysis. It's the asymptotics of this kind of the asymptotic of solution of a linear differential equation as the coefficient in front of the derivative goes to 0. There's the subject of many books. Actually, there's a nice book in the Avanami series about this. I forgot the authors, but it's really nice. So, but again, we don't need, so the precise analysis, of course, is that there'll be some regions in the z-planes when they have like patches with different asymptotics. But this will not important for us now. The only thing that's important is that if I formally remove this, of course, I'm going to get, if I don't, well, I don't know. If you think about it, it'll become obvious. Is that the, well, let's do a equation in one variable. This is already instructive enough. So suppose I have a function. So a function epsilon f prime of z is equal some a of z f of z. Of course, this I can solve, right? So this is this I'm going to say that this is d log f of z is equal a of z divided by epsilon. And so that says that f of z is of the form exponential 1 over epsilon integral of, maybe say, I call a of z the eigenvalue. And so now, imagine that this is, of course, if you're solving a differential equation, then it's not so useful to diagonalize this matrix M. But if you're doing this sort of asymptotics, it certainly is very useful to diagonalize this matrix, because why is it not useful to diagonalize the matrix if you try to solve differential equations? Well, it's because the base is going to change, and so if somehow you will have to differentiate the change of the bases. The eigenbase is going to change. But here, the vector field itself goes to 0. So on the scale of a vector field, the basis is more or less a constant. The change of the basis will be negligible compared to the effect of this. And so anyway, there's some open sets in the complex plane. Well, you have an asymptotics where C of z, some I solution, would be exponential 1 over epsilon integral of the eigenvalue times the eigenvector, times the ith eigenvector. So maybe, what do I call the eigenvector? Called vi z. This is an eigenvector. There's a corresponding eigenvector. This corresponds to each other. So in particular, if I have a formula for solutions, such as the best of course are integral representations. If I have an integral representation, then in the integral representation, I will of course visibly see things like this. This will be just the typical thing in steepest descent. So if I take an integral representation, blow up like this means somewhere in my integrand, I have something which grows like exponential 1 over epsilon, and then this would be location of the critical point, and this would be the value of whatever come from the value of the integrand and the critical point. Now, so if m of z is equal to there's some kind of integral or some space of variables. Maybe call it dx over x. Roughly speaking, there's some kernel function of z, and there's some maybe amplitude a of z. This is a matrix. There's some functions, something like that. Then as epsilon goes to 0, this thing will blow up. We'll have some critical point in x. This will tell you what the spectrum is, and then the restriction of this matrix to the spectrum will give you the eigenvectors. We will get there, but it's easier if you don't worry about if you just care about the eigenvalues, it's enough. If you just care about the eigenvalues, it's enough to look, say, we have a matrix of solutions, a matrix M. You don't care about the eigenvectors, only you want to know eigenvalues. It's enough to know just any row of this matrix. And this is a function, this is a vector. If you only want to know this, then it's enough to know a row of this matrix. It will have all possible functions that occur in the row of this matrix will have different exponential asymptotics. I mean, some span of functions. In that span of functions, we will see asymptotics, and this asymptotics will have to do with the exponentials, with the eigenvector. That makes sense? And so now, algebraic geometry or symplectic geometry provides in general with a solution to a quantum differential equation. In particular, with solution. Also, there are two things here. There is like a Giventhal style solution of the quantum differential equation, and in particular, there's one row in this Giventhal matrix is what's called the J function. So this thing is. This is the J function, just call it J function. So this is, and then integral representations of the solution, that should be a subject of some kind of equivalent mirror symmetry, which I've, let's not go into that direction. So, but there are integral representation solutions, but which I'm going to explain. But I don't know how exactly to fit them in some framework like equivalent mirror symmetry. But let's not talk about that. And so, I'll explain first what's this Giventhal style solution. And the solution is the following. So if I have my space X, I need an operator. Solution is a genetic solution. This quantum differential equation, this Giventhal. So what I do is I study. You can say I study parametrized maps from a parametrized curve into X, but better to say I study maps to like graph. I mean, this is like people call it graphs of maps. So I study the moduli space. So this will be a sum. So everything's be a series in Z. So this will be a sum over various degrees, and so I study moduli space of genus 0, two-pointed curves in X cross P1 of degree some degree D and degree 1 mapping to P1. So it's like a graph of a map. It means it has degree 1 mapping here, so a generic element means somehow. Not generic element somehow. One example there, if I have an actual map from parameterized P1 to X, and I have a map, the graph of this map is an element in here. And so then the contribution from this weighted, so this degree D will give me weight Z to the D, and this is how I'm going to get a series in D. And the variable epsilon will be the variable that acts on my P1. So this is epsilon will be in an element in the Lie algebra of the automorphisms of P1 that preserve 0 in infinity. And the locus at which I want to look here will be some open locus of maps that are really look like graphs near infinity of this P1. So this is, that means I have just draw a picture. So this is my X, and this is P1. It has a point, so there's a point 0 and a point infinity. And so then near infinity, I really want it to be isomorphism, so it looks like a graph of the map. But then it can, like maybe in the fiber over 0, it can break. And you think it can break in other places. And so then my marked point, one of my marked points, will have to sit at infinity. And another one of my marked points will sit over 0. And so this would be, so this is an open set, but if I remember, I have I'm doing a covariant computation with respect to this C star here, which epsilon sits in my Lie algebra. So the fixed loci are very simple. Is that the only fixed locus is then when this part is an isomorphism, and then you break in some way. This is a compact thing, so the equivariant integrals are well defined. So this sum over all D, you take the evaluation, push forward the virtual class times Z to the D. This will be a well-defined series. I call it psi, maybe. Psi. This is a well-defined series in endomorphisms of cohomology of X, localized from power series of Z. And by very, very formal argument, it solves the following equation, that d by d lambda psi z. So it doesn't exactly solve the equation I want, but it solves, it does better. It conjugates this to a constant coefficient equation. So this will be m of z. I'll write m of z, I'll put this. I'll write, okay, maybe I'll write first as a m of z, psi of z minus psi of z, m of 0. And so on this side, this is an operator of quantum product by the lambda, and this is an operator of classical product. And like I said, this is, maybe I don't have time to explain it, but it's not difficult, because what does it mean to take d by d lambda? It means you take z, and then you'd like to insert lambda d here, right? You take this curve and you hit it with a divisor which is pulled back from x, right? So take some divisor on x, lambda, and you pull it back on this space and hit the curve. And so then what's going to happen? It's in this part near this marked point, it looks like a quantum product, right? Because you take a curve and you hit it with a divisor. And near this marked point, there's nothing quantum about it. It's just a classical multiplication. And this is not. It's not. And so in particular, here, the one row about which we care so this is, we view it as an operator is acting from the second mark point to the first mark point. And so if we want one row of this matrix, means we just forget the first mark point, or we insert the identity element at the first mark. So J function is just the coefficient of the row. Corresponding. So it means that P1, we just don't worry about that. And so then, so like I said, there's some general yoga by which you'd like to say that this is an integral of something. And then this means that like I said, like I explained before, this means in particular that will be explained that the eigenvalues come from critical points. So in general, beta equations. So what do beta equations look like? So the equations that we've discussed last week. So they have there's some function. Maybe call it, I don't know. Call it S for an action. There's some function S of some variable integration, some auxiliary variable X, a variable A, H bar, Z, whatever variables others have. This guy blows up as exponential 1 over epsilon S of the remaining guy. And so then you solve the equation of the form so you take the gradient in x of x equals 0. These are beta equations. And these x's are called the beta roots. We will make a connection to what I was explaining before in a second. And then what do you get the eigenvalues? The eigenvalues you get from, so this is, how do you get an eigenvalue? Well, you have to take the derivatives in z, for example. So it means if my operator my operator had a zd by dz. So zd by dz of that function at the critical point. So zd by dz. Right? I mean, just asking what my operator m acts like this derivative. So I'm asking for the eigenvalues of this guy. It just means I have to apply this derivative to this expression, and that will be the eigenvalue. So this is S. These are eigenvalues. This is called generating function of Lagrangian submanifold or something like this, right? You have a So, right, and so now there's the particular, so there's many different philosophies in mathematics that say that the J function should be equal to an integral. The one philosophy that we'll use here is very different. I mean, I guess it's more has to do with like three-dimensional mirror symmetry than the rigid two-dimensional mirror symmetry. So this would be given to us. So this is because, so like I said, the main explanation of this equality. But the one I want to use is because the J function we can also compute using quasi-maps for x instead of this 0 to bar x. Quasi-maps is a different moduli problem. I'll explain. I will explain in a second. So this is some particular compactification of rational curves. I mean, there's some particular modular problem for rational curves. Quasi-maps is a different modular problem for rational curves in X. And the advantage of quasi-maps, they're much smaller spaces. And so in particular, these quasi-maps, they, for example, are, so my X is a JIT quotient. And spaces of quasi-maps are also essentially JIT quotients. And maybe the fixed loci with respect to, let's say, star are JIT quotients. And an integral, the fact that the integral over JIT quotient should be an integral like an ordinary integral, this is I guess in cohomology it's called like a Curwen residue. Is that Herakles? Is that what people call it? What? Jeffrey Curwen residue. Yeah. This is the same thing. So the same thing is also true in K theory. And in K theory, it's more or less from definition. So in K theory, more or less by definition, an integral, an index on a quotient is given by some kind of integral of an expression computed on the pre-quotient. And in cohomology, it's a Jeffrey Curwen residue. Jeffrey Curwen. Is that? Okay, Jeffrey. So this is so maybe the way, somehow to connect that this is, since this is a computation was done by, like I said, this sort of realization that the spectrum is going to give you a beta equation, this was done by Nekrasov and Shtashvili first. And then for them, it's, for what it means for them is something it can be phrased like this. So when people talk about this sort of modular problem, this typically comes up in topological strings, similar. Whereas quasi-maps, this is the kind of modular problem that typically come in the study of systematic gauge theories. So Nekrasov said, well, okay, this is whatever string theory problem is the same as a gauge theory problem. And then in gauge theory, the fact that this is the fact that this is given by some integral is expressed in the form that you first this is some sort of standard computation there. It's you have a gauge theory. You can, well, maybe I'll skip it, but it's not. This is not in the language in which they, if you look at their papers, you're not going to find words like this. But I guess for them, the equivalence between like a string theoretic description and gauge theoretic description, that is understood. And the fact that this a gauge theoretic computation is given by some integral, this is also self-evident thing. I mean, it goes back to at least to the paper they wrote with Greg Moore million years ago, called integrating over Higgs branches. So anyway, so now I'll explain what quasi-map is. So maybe so maybe for Grassmannian. So this is, we understand for T-star Grassmannian, you understand for Eilenberg. So first for in fact projective space. So I have a map from some variety y to projective space, n minus one dimensional projective space. This is the data. This is equivalent to the data. Well, you have a line bundle, and which is the pullback of O of 1, and n sections that generate a line bundle L, a map F. So line bundle L, which is the pullback of O of 1, and n sections that generate L. You have n homogeneous coordinates here, the n section of O of 1, and they generate the line bundle. So this is an actual map to projective space. Now, a quasi-map is a map where you relax the most interesting condition. And this is a map that we... so modular isomorphism. Right? So isomorphism of this data is, if you study maps modular isomorphism, this is the isomorphism class for this data. And so a quasi-map, well, in pedestrian ways, it's just an n-tuple of polynomials. So you take the point y, it goes to f1 of y, f n of y, which now, however, are allowed to simultaneously vanish. So this means I have a line bundle L, which need not be need not be pulled back, just some line bundle plus n sections. Period. Well, I guess they're not identically vanished. That generate L generically. Now, of course, if you have this notion, you can of course define a similar notion of quasi-map to say Grassmannian. So you have a set of a line bundle, a vector bundle. And so if in general you have a map to Grassmannian, you have say, it's easier to pull back the tautological quotient bundle. So then you have a vector bundle plus a bunch of sections. If they really generate this defines for you, it means if some matrix of the corresponding, section is everywhere has a maximal rank, then the really gives you a map to the Grassmannian. Otherwise, it's only a quasi-map. So the general notion is if I have some variety x is written as a quotient of some affine, I mean, it doesn't have to be affine somehow. Maybe pre-quotient, maybe call it, what do we call pre-quotient? I don't know, call it Z, modular reductive group, G reductive. Then a quasi-map. So in this case, we think of projective space, and this is a JT quotient. So we draw it like this. So in this case, you think of projective space as a JT quotient of Cn system. So this then a quasi-map from some variety y into x is the data that you would have pulled back from x if you had an actual map. So means this is the data of the following. So this is quasi-maps. Some variety, I don't know, called B according to x. This is, first of all, you get a principal G bundle over B. So over the quotient, you have a principal bundle, tautological principal bundle, namely just by the fibers themselves. And then this in particular will be like an O(1) for projective space, plus section of the associated, so if you have this principal G bundle and G acts on Z, then you have associated Z bundle, maybe I'll write it, so maybe call it P, and so maybe I'll write it Z cross P mod G. Is that okay? Or is that? So you have a principal, you have a associated Z bundle, and you look for a section. So, and this is modular isomorphism, such that S length S evaluate is stable, generic. And this is a notion, like I said, this is notion in gauge theory, this is a very familiar notion. This is called like gauge sigma model. But a nice paper in algebraic geometry is by Kim, Chekan-Fontanin, and Molik that discusses this notion in algebraic geometry. For particular, they prove the fact that if Z is LCI affine, is L. So if Z is affine, then this moduli space has nice. So LCI and affine. Affine is important for getting this map proper, and LCI is important for have to have a good abstraction theory. B is one dimension. B is a curve. B is now a curve. And you can have marked points on beta, and this is like, right, that you can, and this is somehow, this is some notion that lives over the moduli stack of curves, so that you can constrain. So in particular, Nakajima varieties are of this form, and the Nakajima varieties are quotients of something of LCI affine by reductive groups. So this is just the spaces have very nice abstractions here. And so now, so one can define some counting. And there's some also, there's some moduli space that interpolate between this and that, but it's somehow, let's not discuss. One can define counting using quasi-maps. And abstractly, for any Nakajima variety, you can show that it's going to be the same as counting using stable maps. It's not hard, because you remember how we can, for Grassmannian, we've every argument we made was really something extremely robust, and something which had to do with we never had to look at any loci in which these spaces are really different. We only had to look at curves. We had used some general dimension estimate will be true in any case, and then some vanishing, which again some abstract thing, and then the only curves at which we had to look there, they belong to both. They were really nice maps. They were both. They were maps not even from a chain of curves, from an irreducible component. Yeah. So one can show abstractly it's going to be the same. And so we can define all the structures. You can define the quantum product will be the same. All these things are going to be the same. So in other words, there's some. In principle, there's some complicated wall crossing from quasi-maps to here, but all that wall crossing is just trivial in this case. And so that once you're in the quasi-map world, then if you now look at the so there's some moduli space, but if your domain is P1 and you look at the fixed loci here that are fixed, under this C star action that fixes 0 and infinity, then these loci really are JT quotients. I mean, this is so in general, heuristically, the quasi-map moduli spaces are like JT quotient of the quasi-map to pre-quotient by quasi-map to the group itself. Okay, these are infinite dimensional objects, so maybe you don't want to mess with that. But if you look fixed loci, these are finite dimensional things, and then you just really, these are really, well-defined JT problems. So then you get an integral something which is, okay, maybe, okay, I apologize. I meant to end maybe on time today, but again, I'm making it overtime, but it's, so this looks, if you think about what this quasi-maps on Nakajima variety would look like, it's not that difficult to figure out what's going to stand here under the integral, and that formula for the you remember I gave 2 lectures ago, I gave actual formula for beta ansatz. That formula, just comes directly from, you can just read it off from the geometry of your variety. Because here, okay, maybe I'll write it like this. So here, what you get is like a product of a whole bunch of gamma function over gamma function. And if you take gamma function over gamma function is going to have the arguments of this gamma function have to do something with the tangent bundle to a variety. So then the gamma function has the kind of asymptotics we want is the Stirling formula for the gamma function. So we're going to get some expression which have like x log x in them. And then we take derivatives, you're going to get that formula that formula, the Euler class of the tangent bundle. Anyway, so this is 10 hours plus 25 minutes. So